Take 4 of finite geometry. So let's first look at our axioms or assumptions. So A1, there are exactly 4 lines. A2, any 2 distinct lines have exactly 1 point on them. And A3, each point is on exactly 2 lines. And using these assumptions, we're going to prove that in this geometry there are 6 points and each line has exactly 3 points. So using these axioms or assumptions, let's start with point P, we'll call it. So based on assumption 3, where each point is on exactly 2 lines, here we have a point, and so here we need 2 lines. So I could draw one down here, and I could draw maybe one over here. So right now we have 1 point, and this 1 point is on exactly 2 lines. So A3 is fulfilled, and as well as A2, because any 2 distinct lines have exactly 1 point on them, but A1 is not complete, where it says there are exactly 4 lines. So if we need more lines, then we kind of know that we need more points. And so then we could continue to draw a point here and a point here, because this point is connected by this line. These for any 2 for each point is on exactly 2 lines, so we could say that this point is attached to this line and this line. But then there's problems when it comes to any 2 distinct lines. Maybe this one and this one have exactly 1 point on them. But then to do that, we'd have to probably extend this line. Instead of saying that this is 2 and 3 lines, we could say that this is just 1 and then 2 lines. So we have some more work to do. So then we could start with maybe a point here. Okay? And then we could say that there's a line connecting these two. But then we still have, so based on our assumptions, we might have 1, 2, 3 lines here, although we need 4. So we need more lines, or we need another line, so we probably need more points. So looking at our geometry, we could draw a point, we could draw a point out here, okay? And so we need, based on A3, each point has exactly 2 lines. We could connect this point to here, because then based on A2, any 2 distinct lines have exactly 1 point on them. This one can now have 2 distinct lines, 1 and 2, on this point. But then we still need 2 distinct lines on that point. So what we could go down and connect these 2. But now, so we'd have 1, 2, 3, 4, 5 lines. So by A1, we do not have exactly 4 lines. So what we can do is we can draw another point down here. So this is a floating point, and based on our axioms, we need to connect these 2. So now what we could say is that we have 1 line here, a second line here, so 2, 3, and so to make it 4, we could go like this. Let me just think about this. Oops, I did not mean to move that. But we could go from this point to this point. Oh, and then we'd also have to extend this one down. So this is kind of what it looks like, but let us make sure that we have 4 lines here, and that any 2 distinct lines have exactly 1 point on them, and that by A3, each point is on exactly 2 lines. So I'm just going to use the circle tool here, because we are right now drawing lines, but really lines couldn't be like looping them. And so here would be a line 1. Another line could be 2. See that? Another line could be 3. And one last line would have to be 4. So, looking at each of these, I'll kind of move back here. So this one line has exactly, this point is on, or we'll look at this point is shared between 2 lines, and any 2 distinct lines have exactly 1 point on them, and that is 1. Adding on to another one, we can see that this point is shared among these 2 lines. This point is shared among these 2 lines. This point is shared among, well, actually just one line that's not shared among another one. And that's why we have, let's look at this. 1, 2, 3. Where's my 4th one? 1, 2, 3. Did I not draw it? I thought I did. It'd be here. 4. And so our last proof is we can say that it has 6 points, 1, 2, 3, 4, 5, 6, and that each line, based on this, hopefully it doesn't mess up again, there are exactly 3 points on each line. Oh, there we are. The end.